Hello folks, we are back with our part 16. In this we are doing the problem number 18. Now it's the miscellaneous from chapter 5. This is the part 16 over here where we are doing the problem number 18. Question reads that f of x is modulus of x the whole cube. You have to, I think they ask in the question that f double dash x, the second derivative, is real for all real x. You have to show that f double dash x exists for all real value of x, and then you have to find it also. This can be again done in number of ways, but the way we will be doing it is we will take it in two cases. We will take case 1 where x is positive, and we'll take a case 2 where x is negative. That way we will try to find out what is the second derivative, and that way we'll conclude what they are asking us. Let's get across doing it. As I told you, we'll take the case 1. In the case 1, we will take x as positive. We all know that when x is positive, modulus of x is x. So as a result, your f of x becomes simply x cubed. Why? Because f of x is modulus of x the whole cube, and modulus of x is x because x is positive. So it's x cube. Now quite easy because we have to find the second derivative. Let's find the second derivative. First derivative over here is 3x squared and x raised to n minus 1. So also the second derivative is 6x. X squared, the derivative is 2x. So 3 2s are 6, 6x. So that's it. So second derivative, it exists for all real value of x. Because x is real, automatically f second derivative 6x is also existing. So you can write, therefore if you want, you can make a conclusion for x greater than 0, f double dash x or second derivative exists. So also we can take the case 2. Now in the case 2, you can take modulus of x less than 0. Sorry, x less than 0. If x is less than 0, we all know that modulus of x is minus x by the definition of modulus. We all know it. Then in that case, our fx becomes, because it is modulus of x cube, it will become minus x and then the whole cube. So like that, it is anyhow minus x cube. So you've got the fx as minus x cube. Same way, we will try to find the derivative and second derivative. So let's find the derivative. The f dash x, or the first derivative, as we did before, it will be minus 3x squared. So also second derivative nx raised to n minus 1. It's because of that we are getting it like this, and that way this will come to 6x, minus 6x. That's it. So for x less than 0, the second derivative exists. So also, if you want, of course it's very clear, but then we can take a case 3 where we can say that x is 0. If x is 0, we all know that modulus of x is also 0 actually. Now it's modulus of x is 0 only. So then in that case, what will happen? Our f of x becomes 0. So f dash x is 0. F double dash x is also 0. Anyhow, it's existing. The idea is whether it is existing. So for x equal to 0, f second derivative exists. So in all three cases, the derivative is existing. That's what they have asked us. Just find whether the derivative is existing. We'll have to take up the next problem, and in the next problem they are telling us that sine a plus b is sine a cos, no sorry, the next problem says that d by dx of x raised to n is n x raised to n minus 1. The derivative formula for polynomials, they ask us to show it by principle of mathematical induction. That's a question. So let's do it. We have to find it by principle of mathematical induction. Let's see how to do it. We all know that for mathematical induction, we always do the problem in 2 steps. In the first step, we will show that the result is true for n equal to 1. And in the second step, we assume the result for n equal to k and extend the result for n equal to k plus 1. For n equal to k plus 1, we show it, that this is how it happens. Let's go about doing it. So let's see how we can do it. Question is question number 19. They tell us that d by dx of x raised to n is nx raised to n minus 1, we have to show. This is the statement that we have to show. For our convenience, we always call this statement by Pn. Let Pn be the given statement. So as I told you, we will take step 1 and step 2, and that's how we will do it. Step 1 is always to show that P of 1 is true. What is the meaning of P of 1? Wherever n comes, there you put a substitute 1, and that's your resulting expression. So in this particular expression, what you need to show is, you need to show that d by dx of x raised to 1 is 1 x raised to 1 minus 1. Now they are equal, you have to show it. How do we show it? You take the LHS for this expression. The LHS is d by dx of x actually. X raised to 1 means x. We know derivative of x with respect to x is always 1. So that's clear, it's 1. Now let's go to the RHS of this expression. The RHS is 1 x raised to 1 minus 1, which means it is 1 into x raised to 0. We know by law of exponents that anything raised to 0 is always 1. So x raised to 0 is 1, 1 into 1 is 1. So what happens? We have got LHS equal to RHS, and that is why P of 1 is true. Now that's our first step. To show that P of 1 is true, and extend the result for n equal to k, assume the result for n equal to k, and show the result for n equal to k plus 1. So let's go for the step 2. Step 2 is assume P of k is true. What does that mean? It means that d by dx of x raised to k is kx raised to k minus 1. So what we do is we assume this, and then we show, as I told you, we'll have to show that n equal to k plus 1 is true. So how we will show it? Let's take how to do it. Yeah, maybe to show that. Yeah, to show that P of k plus 1 is true. So that means what do you have to show? You have to show that d by dx of x raised to k plus 1 is k plus 1 x raised to k. This is what you have to show. So we can start from here and show this. So let's consider this. Since we have to show it, let's try considering and doing it. D by dx of x raised to k plus 1. We all know by law of exponents that a raised to m plus n is a raised to m into a raised to n. So there is no harm in writing this as d by dx of x raised to k into x raised to 1. Why we got this? We got this by the law that a raised to m plus n is always a raised to m into a raised to n. It's by that law. Yeah. So we've got x raised to k into x raised to 1. But then that's a product, and we have the product rule. So we can use the product rule. What's the product rule for derivatives? X raised to k as it is derivative of x plus x as it is derivative of x raised to k. So x with respect to x is always 1, we know. And x raised to k, we have found out the derivative. It is k times x raised to k minus 1. Why we got this? We got this from 1. Right? So that's where we have used our assumption. Now let's work it out. This is x raised to k because into 1. Now k is a constant that we can write here. This is x raised to 1 into x raised to k minus 1. Sorry, yeah, x raised to 1 into x raised to k minus 1. Same law of exponents you can do. Add up the powers. See what will happen if we add up the powers. K minus 1 plus 1. It is k. Yeah, so let's write x raised to k plus k times x raised to k. Why? Because we've used the law of exponents. Now x raised to k is common in both the cases, so you can take it out. We are left with 1 here and k here. That is exactly what we require. K plus 1 times x raised to k. So hence, therefore, you can write therefore P of k plus 1 is true. So you have got shown the step 1 and step 2. Once the step 1 and step 2 both are holding, so the statement is true. I'll just write the conclusion here. Running a little short of place, but I'll write it here. From step 1 and 2, P of n is true. How it is true? By principle of mathematical induction. That's how it is. So that's about this, and this is how we are going to go about doing these problems, and that's how this is going to work out. So please go through it, and we'll be meeting in the next video with the next problems. Thank you.